blah, 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 blah.
Blah, 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 blah.
That's my testing. All right, woohoo, everyone's back. Okay. Hi, everyone. Welcome to this week's Learning Space. I am Nicole Gugliucci, your CosmoQuest postdoc, and I'm joined by my co-host all the way this side. I never know.
I'm over here.
It's mirrored. I don't know what's happening. George is over there somewhere in the other hallway.
Yeah.
And so I'm with my and I have with us a couple of my friends from University of Virginia, 2 graduate students. So weird. I can't think of you guys as students because then I don't know. You're like college. I don't know. I'm like, that's weird. You guys aren't students. You're like real astronomers. This is Rachel Beaton and Joanna Corby. You are real astronomers.
That's a good thing.
I'm sorry. I'm tired. And we are going to be talking about their experiences working with high school students doing astronomy research, and how high school students can get involved in different types of astronomy research. There are a lot of different opportunities for that. So if you want to join in, you can ask questions on the YouTube page if you're watching on YouTube. If you're on the event page, I will try and watch that as well, or you can use the question and answer app here on Google Hangouts, so feel free to say hello, send a comment, ask a question, all that good stuff. So why don't we jump right into it? So, hello. Maybe you guys want to give just a brief overview of yourselves and the work you're doing at UVA.
Me go first?
Rock, paper, scissors for it.
Okay. So my name is Rachel Beaton, and I'm a graduate student at the University of Virginia. And I currently work on galaxy structure, both our galaxy and the nearby galaxies, in order to understand broadly how galaxies form and evolve. But I also have big interest in outreach, and one of the things that I started with my actual high school is this research collaboration between a bunch of graduate students at UVA and students at the Central Virginia Governor School for Science and Technology, which is actually in Lynchburg, which is about an hour and 20 minutes from Charlottesville. So I went to that school, and part of the curriculum at that school, it's a half-day program for juniors and seniors that serves 5 counties in rural Virginia, which is meant to enhance the science and technology education for talented students. And a normal part of the curriculum is to do a 8-month-ish long research project in your junior year, where you conceive of the project, you design it all yourself, you do the project, and then you write a full-length research paper that then gets submitted to like the Intel ISIF Science Fair, as well as the state and local science fairs, and the Virginia Junior Academy of Sciences. So I did an astronomy project, and I was one of the first people to come through that wanted to do an astronomy project, and we went through a very, very, very arduous process of trying to find an astronomer who was willing to work with a high school student. And so I actually worked with Jay Lockman, who's at the National Radio Astronomy Observatory, and we had a very challenging time interacting via email. This is still when email was sort of still getting big, you know. And so when I was approached as a graduate student to help with these high school projects, I thought of how important it was in my own career in terms of getting involved in research early and exploring a topic that you don't get to explore, as well as then going to college and knowing that's what I wanted to do and being able to talk with real astronomers, how important that experience was. So I said, yes, let's do it. And later we recruited Joanna, and she can tell you about herself.
All right, yeah, so I'm Joanna Corby. I am a graduate student as well, and I research chemistry in our galaxy primarily. So until about 1970, we didn't think that polyatomic chemistry could happen in space. Now we know there's more than 170 molecules, and we're finding new ones every year, and we don't know how most of them got there. And we know that they give us really important clues to the physics of the interstellar medium, the gas between stars. But we don't really know what those clues are yet because we need to figure out how they got there and what conditions they actually form in. So that's my research side. I did not do astronomy research as a high schooler, but I kind of actually was pushed into this project a little bit by my advisor, who had kind of volunteered and then said, "Ooh, you do it."
Tony!
Outreach was very important to me before starting my graduate work. I have always considered teaching as one of the two components of participating in academia, and I've been more interested in working with K through 12 programs than with college programs because I think that's where the real big problem in the U.S. education system is. One of the really big strengths of this program is that it gives students, I don't care if it's astronomy research experience, it gives them science research experience. And the way we handle science in the K through 12 level isn't really in touch with how science is done. And so I think it's really cool that they get exposure to how science is actually practiced and who scientists are. And something they should come away from the program with is that when they start school, like Rachel said, they should be able to talk to people who are graduate students, who are level, and understand that they are people with cool problems and cool questions.
Cool. So how do you go about picking a research project that's appropriate for a high school student, depending on whether or not they've had astronomy before or computer experience?
Yeah, so that's one of the big challenges. So the typical high school research project, to pick a really boring vanilla example, would be like growing mold on different types of bread, say. So it's something that is
done that.
Yes. So it's something that's relatively contained, where you design the experiment and then you do it. So with astronomy research, however, because of the timescales involved with applying for and then obtaining data, which we all know can take a year or more before when you conceive of a project, apply for it, get the time, and then actually do the observations, and then actually process the data, are much longer timescales than a high school student can conceivably do. So we've actually been utilizing data that we have. So one of the projects came from a huge Spitzer Space Telescope survey in the outer disk, and these were the first images taken in that region, and we actually just had the students go through and find certain classes of objects in that region. So it's just like kind of like Galaxy Zoo type thing project to do. And so the way we've approached doing these high school projects is we take a data set and we figure out a subset of projects that could be done and that are scalable, and then we propose them to the students, so multiple different areas of astronomy, so data we have on hand, tools that we have available, and we let them pick what they gravitate to the most, but we sort of have them choose specific projects that we've worked out. Because one of the key things is that a lot of astronomy takes place in Linux and Unix, not in Windows or Mac. And so getting the students access to proprietary software, giving them appropriately sized hard drives to house data, things like that require some finagling. So we sort of designed the project a little bit ahead of time based on the resources that we can provide. And partnering with the school is really important. For all of our students, they give them loaner laptops that they actually take home. So we install all of the software we need to install, or give them access. Yeah,
this year we actually installed Ubuntu on all of their computers so they can directly work with our Linux systems. So yay for...
Yeah.
I was really excited that they're working on Ubuntu already.
Yeah, and
having exposure to Linux systems directly.
And so obviously what we've discussed is that some of the big barriers to research are learning a new computer system, a language that you're not used to. So we actually composed a set of tutorials that teach them how to do some very basic Linux work, but also give them access to online resources that are good and at their level.
Great, but good.
So it becomes a homework assignment for them to do certain things. and then once they've reached certain milestones, we give them something else. So one thing that's different from college learning and sort of probably being a graduate student researcher is that you're on your own and there aren't assignments. But for high school students, they're very reward-driven.
And this is also part of a formal class, which makes it, which gives us an infrastructure in which to work.
Yeah. That
really helps things to move along.
Right. So one of the things that we learned very quickly was not only do we need to give them homework assignments, but we, at some level, have to be responsible for the grades that they're getting. And that took us a year or so to figure out. Want to grade that much because it's hard. It's weird. But if they aren't held, if we aren't holding them accountable, if it's their teacher, then they tend to treat us differently than if we're holding them accountable for what they're doing.
Okay.
There's different standards involved. So that's one of the big barriers. And the other barrier, which I'll let Joanna talk about, is getting them astronomy knowledge.
Here we go. I mean, astronomy is not that intuitive. It's something that everybody can be exposed to because everybody has skies, especially in the rural counties of Virginia. But there's a lot of units that we use that are not. So basically, Rachel was involved the first year of this program, and the second year it was a larger group of us. It was 4 students who were involved, and that year a lot of things were really figured out. And after the first year, it was clear that they needed some simple astronomy instruction before getting into anything else. Needed to understand something about the telescopes that they're using, something about the data that they're actually looking at, a lot about light and spectroscopy and what you're actually looking at when you're seeing a spectrum. And then there's a few other things that you just kind of brush over, like Kelvin units in radio data.
Yeah.
So you come across things where you're like, don't
temperature is brightness and brightness is temperature. Just go. Sorry.
But it's really gotten pretty well figured out so that we end up spending about a month going through basics of astronomy and spectroscopy. Because this is a remote program, we live in Charlottesville, they go to school an hour and a half away. We only meet with them a limited number of times, usually about 3 or 4 times over the course of the entire year. And so we make sure that one of those times comes at the very start, and that we go through a lot of discussion about spectroscopy, about light, about telescopes, and all of the lectures or all of the information is very interactive there. And then also break apart and do some project-specific things.
Yeah, so we put together, well, ideally we have a weekend with the students where they actually come to Charlottesville. It doesn't always work out, so it's modulated quite a bit depending on the schedule and the snow and all that kind of fun stuff. But the idea is that we give them an astronomy boot camp where we give them as much hands-on lecture material as possible, sort of at a first-year undergrad-y type level, but also going deep on the really important concepts that we really want them to take home, like light and spectroscopy and all that kind of stuff. And actually let them interact with the material. So we do lots of our hands-on demos with them, and the same kinds of demos that you do with younger classrooms, but this time they're thinking about the deeper concepts when we do the demos.
And you're discussing the deeper concepts. And we also have them do kind of work as a team to develop concepts in tutorials together. And that's something we usually have of order 4 to 6 students, and we typically have them working on 2 very distinct projects, so a few of them are kind of working together on one project, maybe with slightly different data, but the same ideas apply. And so having them actually begin to rely on each other and realize how they are each other's resources in that setting where you can supervise them just a little bit is a really good thing for them working together throughout the year.
Yeah, something that we know from being graduate students is that research is a lot smoother when you're in a research group where you have peers that you can rely on, or people that you go to when you need help. And so we try as much as possible to make, so we only do 2 sort of flavors of project every time, because we want them to work together as much as possible, and we want them to feel like they're a research group almost, and we're like the head of the research group. Precisely because we can, if one of them really understands how to fit a spectral line, then they can help the other person fit it, and then that takes a lot of the pressure off from us when we're doing frantic Skype conversations in the middle of the night. And so along with that is we try to do a weekly group meeting with the kids, which is a Google Hangout like this, where sometimes it also helps when someone's not in Charlottesville so that people can call in, and the students are supposed to prepare weekly reports. And the idea of the weekly reports is that if someone can't come to the meeting, say their direct advisor, that they can read the report and then respond in the Google document. So it's a Google document where you can leave comments and all that kind of stuff. And the objective of the reports is for them to talk about what they've done and discuss their problems, and also let us know when they have 4 tests and a track meet and a band concert. Because those types of life events, actually, we don't want them to come away with this with a negative experience from their research. So being flexible with their schedules and their stress levels, we've found is really important, and they begin to trust you a lot more when you behave like a normal person does. So we're really flexible with them, and we have schedules and due dates and all that kind of stuff, and we use the weekly meetings to remind them about what's coming up, and make sure that they're aware and they can get what they need to get done. And also, one thing that I've noticed about group meetings is that when your peers are with you and you're talking about how you didn't do anything, you kind of self-regulate the amount of work that you should be doing, which tends to help, I think.
Yes.
But keeping them focused during those meetings can be really hard.
Finally, we talk about concepts quite a bit in those as well. So any issues they came across, we kind of try to beat through them, and we try to ask them questions that show us that they're thinking about the material and show us where they're coming across.
Yeah.
Are there teachers involved in what you guys are doing, or is it pretty separate? Are you guys kind of on your own to guide the students?
So they have.
I missed the puppies. I'm sorry.
Sorry.
Nicole knows that dog.
Yeah, she's an intruder. They live here, though, so it's okay.
So she asked if how present are the teachers in doing this. So during the Skype meetings, the teachers are not there. There's one main teacher that we've been working with for the past 4 years. This is the 5th year of it. And she's really wonderful to work with, and she communicates with us typically at the end of every few Skype meetings, and we'll very comfortably email back and forth and have developed really a good relationship, and she's really willing to work with us on everything we need. You know, we don't want them sending us papers with ridiculous numbers of grammatical mistakes, so she will hound them about that before they come to us.
So the way their day is structured, and sort of our program is completely built around this situational factor, is that every day they have about 45 minutes or so that's research time. Okay. And some of that time is actually guided instruction by their teacher, so like how to make a graph, how to read a paper, lots of things where they're just learning what research is. And then they also have free time where they're supposed to work. And so their teacher is actually doing the sort of day-to-day management, crisis management, if you will, with the students. You know, things like, I lost this, or my computer doesn't work. Yeah. Because we just can't handle that. Our schedules are not aligned in such a way that, so these students are in class from 7:30 until 10, I should also mention, in the morning, which for your average astronomy graduate student is not our peak mental practice. So,
yet.
So we can't handle the sort of things they come across, and if they have a computer issue, you know, the earliest it would be resolved would be the next day, and usually we need to get more information from them. So one of the skills, you know, if we think about our major skills that we're trying to get across, we're also teaching them good communication, how to talk, how to write an email that expresses your problem so that I can help you with it, how to
I type this in and I get this error. Or this won't work, right? They give us this won't work. And you say, well, so we talk about how do you
troubleshoot? Yeah.
And I guess the other thing to keep in mind is that the end game of this whole process is to have a research paper, which is,
for the journals or for the
Virginia Junior Academy of Science. So there are various restrictions on what they have to do. And also they put together a poster and a 15-minute talk, I think.
Just a 5-minute talk.
5-minute talk.
So they put together a poster which goes into science fairs. They put together a paper that goes into science fairs. And then they put together a poster and a talk which we present at the astronomy department and at National Radio Astronomy Observatory in Charlottesville.
I've seen at least one of them. Yeah.
Yeah, we have a whole high school research day, and we make them researchers for the day, and it's actually really fun, and everyone's really good spirits about not.
Yeah, professors are very supportive.
Yes.
So they'll come in and ask them questions, and if they come upon stumbling blocks, they'll kind of work them through it, and it's nice, I think, for them to interact with some other people about science besides us, just because. Because we're their teachers in some way, and now these are random scientists who think they have done a wonderful thing.
Yeah. So our sort of astronomy curriculum is based off the curriculum that they would go through if they were in their school. It's just that we have moved things around so it makes sense for their projects. They spend a lot more time doing background material than the average high school project, whereas the average high school project spends a lot of time on experimental design. And methods. We sort of spend more time on backgrounds than they do, and we do that first. And part of their curriculum, which is really fantastic, is that they actually are writing their paper as they go along. So when we've gotten through the background for their project, we have them at least outline at least some sort of draft of their introduction for their paper. When they learn all their methods and their data, they write the data and methods sections of their paper, so that when they get to the end and we're rushing to get results together, they do have something that they can literally just sort of core dump into a document that we can work on. And then we revise. And one of the things we've learned about high school students is that when they turn something in, they think it's done. Getting them to understand that turning it in is just the first step.
Yeah. Oh, wow.
Has been really challenging. So we have to build in reward metrics where it's like, well, we're going to grade this really harshly, but everything that you go in and fix, you get points back, say. Or if we have to build in all these sort of structures to encourage them to realize that when you turn in something, it's not finished.
Yeah, and again, it's a really good thing that they come. Basically, they write their paper through February, but they've already written most of the parts during the fall or during January when they're still closing up the actual analysis and have done the background. But getting them to understand that those are still fluid documents. So instead of just taking everything and stapling it together, which is great, you might come out of the analysis portion thinking, well, maybe my introduction wasn't actually that relevant, and so that's another step that high schoolers don't make that a little.
Yeah. Are they all writing individual papers, or do you ever have teams or pairs, or is it all individual?
Their papers are all individual.
All individual.
And so there's a huge gradation, and it has a lot to do sometimes with, is English their first language, to how well do they understand the project. You see a lot of variations between the papers. Sometimes you get a paper, so the past couple of years I haven't been as involved in the day-to-day mentoring, but I have proofed their papers just to have a different set of eyes and a different set of feedback. And last year I actually had a paper that read like an undergraduate thesis almost.
Wow.
And it was beautiful. It wasn't all in the right direction, but it was beautiful. So you get this huge, you can have students who just knock it out of the park, and you have some that struggle for various reasons. And sometimes it's term confusion. So they're just a little bit confused about how to use specific terms, and they use them improperly, and that's a huge stumbling block for them. Even things like, is this a plural word or a singular word, and what does this really entail? That can be a problem, and sometimes it's the writing skills, but we're always pleased with what they do.
So we have a question from Tom, who is asking, do you find high school girls getting into science these days? He says, in times past, it seems girls didn't want to be considered smart to their peers. So how does it work out, the gender balance in the program that you've seen over the few years?
So I think part of it is that students who go to this school are required, and so the filtering are required to take the research course. And everybody who's at that school is smart. And I think that it would be hard to go in and find. This is a specialized school for people who are talented in math and science. So you would probably see a bigger problem with this if you were just at a random school. But in this environment, we see nearly equal representation.
I mean, we only get 5 students a year, but I mean, there's always a girl. Sometimes it's more girls than boys.
Yeah.
It just varies depending on the set of students. I mean, so the students choose. We do a presentation over the summer about what astronomy research is and the types of ideas, and it's very important, we think, that the students want to do this program, and they're also warned about the level of independent work that is involved. So there's a little bit of filtering there too, and we tend to get students that are pretty well motivated and they really want to do this project, but we don't see a lot of gender breakdown in that. Yeah.
So this year it's 4 students that we're working with, 2 girls and 2 guys. And last year I think it was 5, and there were 2 girls and 3 guys.
Yeah. What are the science that they're working on currently? You said there were kind of 2 modes of 2 science projects.
So right now they're working on one. So it all comes down to what data do you have, and because we're at UVA and work with NRAO, National Radio Astronomy Observatory, which I'll just call NRAO.
It's fine.
Because we're at NRAO, there's a lot of people with a lot of data around, so we will crowdsource them for data and for straightforward project ideas. This year we are working, the students who are working with me are working with a data set that my advisor, Tony Ramajan, was largely responsible for. It's called the Prebiotic Interstellar Molecular Survey. It's a whole lot of data towards one source, molecular cloud with regions of ionized hydrogen, and these students are doing Gaussian line fits to the recombination lines. So this is a general audience, yeah?
Yes. All the molecules. All the molecules in space. Yeah. General audience / CosmoQuest people / educators. So yeah.
Okay. So yeah, you have these fairly large regions of where all the hydrogen is ionized. So in space, most of everything is hydrogen or helium. All the hydrogen is ionized, and basically you have electrons roaming around, and you have the protons, random walking, and when they collide, they recombine, right? So the electron and proton become neutral hydrogen, and basically it's very quickly reionized because there's high energy ultraviolet radiation that's coming to bust those proton and electron back apart. But in this very short meantime, the electron actually recombines at a really high electronic state, and then it just falls down. And so with each one of these falls, you see a spectral line. So they're looking at these spectral lines from that, and I can quiz them on most parts of the basic concept, and they do wonderfully on that. And they do. We went through a very simple derivation of Doppler line width, very simple. So they understand that the width of a spectral line tells you something about the temperature, and they understand the relationship there. all of the constants, and there's a lot of fudge factors that go in front that have to do with the specific physics, which I am not going to feed to them.
Yeah, I remember the ISM course. Blah.
Yeah, but the very simple relationship is quite easy to derive, and so we did that in an entirely interactive way where I kind of had a blank PowerPoint, you know, like one slide would be blank, and then I would have them basically get the answer that would be on the next one, and we went through it. And so they're doing Gaussian line fits using the programming language GBT-IDL, which is used to deal with radio data.
And it has a really nice visual fitting tool, so that the students can see what they're fitting, and it spits out numbers. It's a really beautiful tool, and I didn't know about it until I started working with this project, and I realized how wonderful this particular tool is. And we use that one a lot because it's so visual, and it's really easy for the students to follow.
Yeah.
All things considered, it's very easy.
So this is using the Green Bank telescope, right? That this data.
Yeah. So this is all data using the Green Bank telescope, radio data, and it's spectral. So you have intensity or brightness versus frequency, or versus wavelength, I guess. And actually, both projects. So that's one project that a couple of the students are working on. The second project right now is mega masers.
So
really? They're doing that? I'm so excited.
Yeah,
Jim Bratz's data.
So actually, we're using some of Nicole's data that she took.
Oh my God! That was like my first.
And so we're working with Jim Bratz at the National Radio Astronomy Observatory, and he studies these things called mega masers, which they're like lasers, but they're in the microwave. And they're
not
emitting...
in your kitchen microwave, like in...
No. In the microwave part of the spectrum.
Sorry, I just imagined my laser pointer in a microwave when you said that.
No, that was very bad, actually.
Don't do that.
Don't do that. No, so we happen to find them in the accretion disks around supermassive black holes. So supermassive black hole, there's this region around it that forms a disk. And that matter eventually goes into the black hole. It's its lunch. That's what it's eating, and that's what ultimately makes it bigger. But around a number of black holes, they found these mega masers in the accretion disks, and they're basically just regions that are getting a lot of energy pumped into them at the right frequency so that they emit a highly narrow range of energies. Is this right, Nicole?
I think so. I'm looking up images while you talk, because this one I know.
Yeah, okay, good. So a spectral line
from water, which acts like a laser.
Which acts like a laser, and they're really, really powerful. So they're called mega masers because they're 10 to the 6th, or mega, times, a million times more powerful than your normal water maser in the galaxy, which are just in little molecular clouds. So these are super powerful regions.
Here we go.
And they found that using these... Oh, yep, there you go.
There's the classic model of NGC 4258. So this is the disk.
The accretion disk around.
Yeah,
around the black holes in there somewhere. And then the spectrum you get out, you see the red-shifted masers from this side of the disk. You see like a peak in the central part. So this is whatever velocity the galaxy itself is at. That are right in front of the black hole, and then the ones that are blue shifted. These little tiny ones here, so you can actually see those regions as they're lighting up and giving off that microwave radiation.
Yeah. So the really cool thing about these accretion disks is that they move in what we call Keplerian orbits. So just like the orbits in the solar system, and that you learn in your basic physics class. And so by actually measuring their velocities, and because radio data can get very precise positions, you can actually figure out how quickly they're moving around that black hole. You can actually figure out their precise radius, and then you can figure out the distance to that galaxy very, very carefully and very, very precisely. So these mega masers are phenomenal tools for understanding how the universe is expanding, because you get very precise distances to specific galaxies. Mm-hmm. Unfortunately, we don't really understand why some galaxies have mega masers and other galaxies don't.
Which is
And
why
so
we
Jim
looked
Brown-
at all the galaxies.
Yes, so with Nicole helped with this. They looked at all the galaxies that had features similar to the ones that were first discovered. And then what Jim did with some collaborators is he actually went out and got optical spectroscopy, so in the type of light we see, not in the radio, because traditionally these supermassive black holes have been identified and studied in the optical. I don't know why, but a lot of the metrics and the way that you decipher what type of what type of supermassive black hole, what flavor you have, is using these optical spectral diagnostics. So he went out and got data for all of these galaxies, and we have actually had the students do line fits, just like they're doing with Joanna, to measure these spectral properties and then compare them to larger samples of other galaxies to see why are these megamasers different, why might this be happening. Mm-hmm. And then we've also had them fit all of those little emission lines that Nicole showed you. We had them go in and fit them.
Again,
and actually figure out all the velocity components to better understand the accretion disks themselves, and to even look for mist, very faint and mist emission that they might not have found using the sort of general tools that astronomers use. So to do it galaxy by galaxy and very, very carefully, whereas in this huge survey with thousands of galaxies, you just sort of run a blind tool and you might miss something. Mm-hmm. So the students have been doing little chunks of these parts of this research and doing really well, too.
That's excellent. Yeah, because there was at least one in that survey that we found that wasn't classified as an active galaxy at all. So it would have been missed had we not been looking at every freaking galaxy in the sky. So you never know which one. That's what it felt like. So yeah, they come up in unexpected places, and they still need an order of 10 of these galaxies in order to do the dark energy project. Is it still in that vein? Yeah, they're looking to get better estimates on dark energy. Oh, I'm so excited! I didn't know they were using that data. That's great.
Yeah, it's been a really fun project to work with, because you get a lot of students who want to work with black holes. Yeah. They want to know about black holes, and so now you're saying, well, we're not going to learn about black holes, but we can use black holes to do this research.
And you can do very simple physics to get an estimate of the black hole mass. Yeah. So there's a few assumptions that go into that.
Yeah, we had them do that.
But they obtain black hole masses, and they
compare using different lines, and do you get the same mass? They did all sorts of interesting things.
Cool.
Yeah, in spreadsheets, in Google, in little spreadsheets. Yeah, they're doing.
So spreadsheets are nice because that's one thing that you don't have to teach them, and they might teach you.
Yeah.
And then I think it's cool to focus on Linux as what they should learn for new computing.
Yeah.
And there is a computer science teacher on a computer science class at the high school, and they're actually switching to Python soon. They have been using Java. So when they switch to Python, this whole thing could explode, because they could actually maybe learn how to write some of their own little programs.
And there's a lot of astronomy being done in Python. Yeah, not so much at UVA, but there's a lot of astronomy being done in Python, so that'll set them up really well for that.
There is at UVA, though.
Oh,
yeah, we're moving.
Oh, you're moving there? Okay, I know. I just know that because you mentioned GBT-IDL, that uses the IDL package, which is proprietary, which you then have to pay for. So it's good that you can offer that access to the students, whereas they might not have access. I say that because I don't have access to IDL anymore, and I'm really sad. So, actually, this is related to a question by David McAllister. Are the data your students use for the project available to other students to use? Are these types of projects available elsewhere? I would say, the data itself probably is public, but is it easy to access?
Probably not, actually. Yeah. So your data is obviously...
We make our data reasonably available, and we're making it much more available in the very near future. And we help anybody who has a project if they want to use our data as well.
Okay.
So that's the Primos data.
I think the data, the optical data the students were using, I think that is on a public website, but probably figuring out how to use it would require, it's probably not in a form that you could just pull off the shelf and use.
Right.
But certainly something that's clear with working with us and with us crowdsourcing from NRAO, and also with the rest of the class who's not doing astronomy, is that usually if you want data from somebody or you want some project ideas, you can communicate with them and get them.
Yeah, so one thing we didn't mention was, in addition to all the projects that we're doing with astronomy, every student, so I think there's about 40 or 50 students per class, they're all doing projects, and almost all of them are partnering with an institution like UVA or with a community member or with a private, so there's a lot of engineering firms in the Lynchburg area with like farmers, most of their projects are actually partnerships with people that are out there. So I think the lesson to learn is that if you want to do a project, you just knock on doors and you'll find someone who really cares about it and will help you.
Okay.
Unfortunately, doing these high school projects, it does take a fair amount of time, and I think it takes a fair amount of expertise in knowing what you're doing in terms of communicating with the students. And also one thing we've learned when we've tried to take it to other schools is the situational factors. So is there a teacher there? How much time do they have to spend? What's the setup? Can we communicate with you? All of those things are really important in terms of making a successful project. So as much as we really want to adapt this to other schools and other situations, it seems it can be a little bit of a challenge sometimes.
Right. Yeah, you want the teachers to be trained on it since they're going to be dealing with the students more often.
Right.
Yeah.
And you need to spend a certain amount of time a week too to make it productive.
Yeah, they don't necessarily need to be, the teachers don't necessarily need to be trained on astronomy, but on methods of research, to know, of course, that your science teacher should know what a science paper will look like, but really to have it well organized and have an infrastructure in which somebody can just really focus on the data and on the project. Certainly doing it in a class environment makes it really much more doable for us.
Yeah. And then the other side of this is actually, getting to a point where you give a student a project and you've sort of thought it out and put it together nicely, and then that project.
Georgia, did they freeze for you?
Yes.
Oh no, you're still there.
Oh, okay, there they are.
Okay. So what I was saying is that moving our work.
Oh, it's still there. Okay.
No, we see you.
Still there?
We hear you.
Okay.
Yeah, go ahead.
Getting to the point where we can give a student a package project, and get back results that we can then fairly quickly use, has also been a higher level goal of ours, and we're still moving there. We're not quite there yet.
Right.
Yeah, I was
so
gonna ask
some
you
of the
guys.
projects that we started with 5 years ago are nearing. We've published one of them, and we're close to publishing a second one.
Okay.
But basically, we use the students as feelers to explore something that we're not really sure if it's going to turn out to be interesting, and they usually tell us, is it interesting, is it not? And then we have to go back and use their results as a guide, but we usually have to do things a little bit more carefully and uniformly, I guess, is the other thing, before it's ready for publication. So I think, looking towards, if you want to find more scientists who want to do projects with high school students, learning how and being able to communicate with other astronomers who've learned how to do this well and have it turn into science that's good, is one thing that the community would use in order to make this a broader outreach thing.
One thing I might suggest is the Pulsar Search Collaboratory, which is also run out of the National Radio Astronomy Observatory, because they have lots and lots and lots of high schools that already work on that project. So that's something where I think they have an infrastructure that you can plug your students into. I don't know deeply about that. I don't know if either of you are closer to that
Yeah, it's a 2-week camp over the summer that the instructor has to go to.
Okay.
Certified. And then I don't remember if the students have to go or not, but I think there is one where the students go to.
Okay.
And then they can continue working through the school year on that as well.
Okay.
So that's a nice one.
Because they built
my
an
collaborator.
interface.
Yeah, my collaborator runs a residential program in California at the University of California, Santa Cruz, which is a residential summer program for students to do research.
Okay.
But that is not a year-round program; it's just in the summer, and it's called the Student Internship Program. And that's been working really well too. And sometimes the students continue through the semester, and sometimes they don't.
Okay.
So one last thing that I think is worth mentioning is well, I started this when I first started my grad school, so the very first year, and I didn't do too much to design the project that year. My advisor did most of it, but in the following years, I've designed the projects that they do for the astrochemistry work, and that's a really cool thing, I think, for a graduate student to do, because at every point in the academic's life, right, you're doing the job that you have now, but the next job that you're working for is totally different, right? So getting some exposure to advising and to thinking about how you build a cohesive project that can be done within some time frame is really important, not just for planning for other people's projects, but also planning for your own.
Yeah, you learn a lot about your own workflow management when you're thinking about your high school students. Like, what is their next step, and how do I get them to think of it without me telling them, or how do I, how do I step them through without just telling them everything?
So you're getting great advisor experience, faculty advisor experience already.
Yeah.
They're very basic, but yeah, certainly.
That'd be good.
So I guess we should mention that we're bringing, for the first time, we're actually bringing our high school students to the American Astronomical Society meeting in Washington, D.C. because it's nearby and it's a tractable grant to write. So we actually have money to take 8 of the students and their teacher to the meeting, and they'll each have there'll be a Mega Mazer poster and a chemistry poster.
I'm so interviewing them. I'm gonna embarrass them.
They're gonna be there the whole day, and it's the day I'm giving my talk, I think. So we've planned this whole day with them, so we're really excited.
Awesome. Oh, I'm looking forward to that. Good. Yay! So there you go, AAS. Anyone going? Come check it. What day? Do you know what day of AAS that is?
Wednesday and Thursday. So they'll be there all day Thursday, and I think they'll make part of Wednesday.
Okay, cool.
Yeah.
Very cool.
And there's actually a special educator rate at the hotel, which is very cheap. And there's educator rates for registering for the conference and stuff. So
very cool.
You'll sometimes see high school students there. There's actually a program that trains teachers to use high school teachers to use Spitzer data, I think. And I ran into them we do a poster every year on our program, and you run into other high school mentoring programs, and you learn a lot about how they work. So I think that's also a great, that's also fun to see how other people do their programs.
Very cool.
So are you prepping?
So this year we will have something on our program, and then they'll have 2 science. I just said the number.
I know. We're a little nervous about if there's going to be 2 posters or not. So
they will have science posters.
The plan is 2 posters, but
Gotcha. Okay.
If we have enough to fill 2, we're not sure.
Oh, so Tom Nath is asking, so it helps if the students know Linux, spreadsheets, Python, technical writing, but it sounds like you teach them a lot of this along the way as well. They don't have to come in.
Yeah, we teach them a lot of it. Yeah.
Okay.
It helps that they have access to those resources. I would say, like, the first barrier is, do they all have a computer that they can use? Do they all have an internet connection? Can they log onto our servers? All that kind of stuff.
Right.
And we try to use as much open source like Ubuntu and Python as possible because that's really easy to get in everyone's hands.
Yeah.
And since we are working in a rural area, we can't always be certain that our students will have internet access from home, or that they will have a computer at home, and we've run into that before as well. So I'd say one thing that the school has really helped us make sure that the students have what they need at each stage while at school, and then they can take those home if they can. So we work really hard to make sure the students can be self-sufficient with those tools. And they learn in high school now to do a lot of the spreadsheet and the writing.
Okay.
Yeah. So.
But it's also really cool how far a few tutorials can go at getting you able to use Linux.
Yeah, it's not hard.
There's only, I mean, how many commands do you use?
Yeah.
More than 5 times a day, right? There's a few handfuls.
Yeah. Awesome. I have putting a few links on the Hangout page, which I'm going to try and screen share really quickly. So I found the link to Primos, I think. Joanna, you can correct me on this. It's I don't want to read this whole thing.
Under construction right now?
Yeah, it's the under construction. But if you Google Primos, Primos, and astronomy, I think it comes up. But I've put all these links on the Hangout event page if you want to check that out.
Yeah, there's a nice article in Discover a couple of years ago that I think talks about Primos.
Oh, okay.
Or one of the pop science magazines they've put out some really nice articles, and Tony has contributed to them.
Yeah, and the recent NRAO, was it a press? It wasn't a press release, but it was a video that was done by Tanya.
Oh, okay, yeah,
Tanya Burchell?
Yeah, Tanya.
Awesome. I love Tanya. She's the one who's getting us together with NRL to try and do some citizen science. So we may have you guys out there doing this stuff too, not just torturing high school
students. Yes, and the NRAO has just hired a STEM outreach facilitator for the first time. So we're hoping, that's going to be a fruitful relationship and build on some of the programs that we started.
Because it's radio astronomy and it's citizen science, and it's just like my happy dream come true. So we're working to get that started. And then also I just searched Pulsar Search Collaboratory. I don't think too many people use the word collaboratory, so that's pretty easy to find. PulsarSearchCollaboratory.com. That gives you all the information on that project and lists all the different schools that are involved in looking for pulsars using GBT data. And then I also found a link for the UC Santa Cruz summer internship. I put that up there if you want to check that out for people in that area. Any other resources you guys can think of? Programs.
So in terms of citizen science, sorry. The Sloan Digital Sky Survey, of course, has Galaxy Zoo and the Zooniverse programs where you can actually help with research. A lot of the work that we started with the high school students is now part of the Milky Way project, where you can go find star clusters for us. And then I know that there are a lot of projects in the works to do more citizen science and get more data out there, because you can actually use these citizen science venues for your student research, to have them classify galaxies and spectra and all that kind of stuff, and then, there are some questions you can ask from there and put together a project, and so that's another really nice way to get access to data, if you want to do some explorations on your own, or find someone to help a project. You can always suggest there are resources out there.
Right. And citizen science projects like CosmoQuest and Galaxy Zoo are built to work in a browser, right? So you don't really need a special computer to look at the data. So that stuff's already built. And I think even the Pulsar Search Collaboratory, does that work in a browser? Or I
think so.
I think that works in a browser as well. It's a bit more complicated than most citizen science projects you'll see out there, but it's made to be very portable so that your students can use that pretty much anywhere.
Yes.
Very cool. If I had to do it over again, I'd do pulsars. Pulsars are really cool. That's just me. Any other questions, Georgia?
No, I had one about 10 minutes ago, but it's gone.
Whee! Gone from the head. Gone from the head. Yeah, I was gonna say neither of you have secondary education experience. This is your first time. You're kind of thrown in with high school students for the first time. What is that like for you and your development as educators?
I think the teachers at the school really helped us,
Mm-hmm.
And they gave us their curriculum.
And they allowed us to adjust it according to what you actually need to do an astronomy project.
And they would give us so the students sometimes won't tell you, oh, that was too hard, but they'll express it to their teacher, and their teacher would tell us. So we would get a lot of like gossipy type feedback on what we were doing, which was really helpful from the students. In terms of, I think it's been a really rewarding teaching experience because it's a challenge sometimes to convey really complicated concepts.
Mm-hmm.
And it actually helps you explain your research to even academic crowds that may not be versed in what you're doing.
And it helps you understand all of the assumptions that you're making, and also all of the subtleties in how you handle your data that you kind of, we don't even have to think of. They're second nature, right?
Right.
So in some way it makes you appreciate what you can do and think about how you break down complicated concepts.
Yeah.
And complicated series of actions and an analysis.
Yeah, and of course critiquing other people's writing is always a great way to learn more about writing and get practice.
And it's fun when we get to see them. Also, they come up, when they come up and they learn, they tend to have a really good time.
They do.
In spite of the fact that we are making them work.
And then a lot of them have actually come to UVA because they are Virginia students, and this is one of the big Virginia schools. And so you'll be walking on campus in your, nerd space, like all thinking about work, and then all of a sudden one of them comes up and gives you a huge hug. Like, whoa, I don't know undergrad. But they continue to be appreciative, I think. And even this, so we've had several students. One student is in aerospace. One of them is actually an astrophysics major at Ohio State University. But we've had several students who pursue astronomy. We've also had several students who don't, but have a huge appreciation for astronomy and for research and for science. A lot of them want to be writers or photographers or something, but when you talk to them, they want to spin science in there somehow. They want to write more about science. They want to take pictures with more. They want to know more about optics and light and all that kind of stuff for their pictures, and perhaps are going more sciencey. So we feel like we're doing pretty well.
Awesome.
It's very rewarding.
You're boosting the STEAM. You're boosting the STEAM community with that.
Yeah.
Right? Yes, Rachel is also. Yeah, it's STEM with art. STEAM. Oh, this is a thing now. Yeah.
It is?
Yeah. You're also a photographer, Rachel. So there you go.
Yeah.
You can work that in. STEAM. All right.
I like it.
Yeah. So we are almost up to the hour. I'm going to do some brief announcements and then maybe give Rachel and Joanna a chance to sign off with, maybe your favorite moment teaching the high school students, like something that they really went at. But I'll do some announcements first while you guys think of that. Tomorrow we are doing a special Google Hangout on air with the some of the Dawn Science team. This is, I have to find the name of the actual event. It's something with Hubble. Okay, Dawn Mission, Hubble Inspired. That's the name of it. I'm like, I know there's Hubble. We will be talking to two scientists who are working with the Dawn spacecraft, as well as Brittany Schmidt, who's also a scientist working with Dawn. We'll be talking with Max Mutchler and Jianyang Li, who are using Hubble Space Telescope findings They compared some of the Hubble findings from Vesta to the Dawn images of Vesta, and what we can expect to see at Ceres when Dawn gets there based on the Hubble data they've taken so far. They'll also be talking about satellites, so moons around these asteroids. And one of the gentlemen who will be joining us is the guy who discovered the second and third moons of Pluto. So we'll be talking. I'm sure I'll find a way to work in a question about Pluto for that. So join us. That is tomorrow. Google Hangouts on Air. Dawn mission Hubble inspired. It's at 3 p.m. Eastern, 12 Pacific, and 8 p.m. Universal. I think I've got the main time zones down. So check that out. Friday is the weekly space hangout. Fraser Kane will be hosting a bunch of us talking about astronomy news for the week. Probably crying over ice on some more since we missed last week's weekly space hangout. We'll be crying over ice, and that's at noon Pacific on Friday. Sunday night, virtual star party. Monday is astronomy cast, which brings us back around to Wednesday and Learn in Space. So hope you guys can join us for some of those hangouts. And Rachel, Joanna, do you have last thoughts you wanted to end with?
We're having trouble finding a single favorite moment. But it's certainly got to be the days that we actually see them,
Nice.
and they become humans, and we become humans.
If
Not just
if
emails.
you play with them and you play Cards Against Humanity and things like that with the students, and they're real people. Yeah, it's been kind of fun with them. That's the best part.
And it's when you see them standing tall in front of scientists and talking to you're celebrating what they've done. You're allowing them to celebrate what they've done under a slightly high pressure environment, and you're also celebrating what we did in our department. So everybody comes in and sees them, and when they understand concepts and can explain them to our professors or to real astronomers, that's just, I feel like that must be a really cool thing for them.
Yeah,
and it is for us.
Yeah, seeing them explain their research to other students, even other high school students, is also pretty cool, and they do a good job. It's like the biggest warm and fuzzy ever.
Warm fuzzy astronomy! I love it. All right, thank you so much, Rachel
thanks,
and Joanna
guys.
Corby, for joining us on this week's Learning Space. I will see you all next week.
All right. Bye-bye.
Rock, paper, scissors for it.
Okay. So my name is Rachel Beaton, and I'm a graduate student at the University of Virginia. And I currently work on galaxy structure, both our galaxy and the nearby galaxies, in order to understand broadly how galaxies form and evolve. But I also have big interest in outreach, and one of the things that I started with my actual high school is this research collaboration between a bunch of graduate students at UVA and students at the Central Virginia Governor's School for Science and Technology, which is actually in Lynchburg, which is about an hour and 20 minutes from Charlottesville. So I went to that school, and part of the curriculum at that school, it's a half-day program for juniors and seniors that serves 5 counties in rural Virginia, which is meant to enhance the science and technology education for talented students. And a normal part of the curriculum is to do a 8-month-ish long research project in your junior year, where you conceive of the project, you design it all yourself, you do the project, and then you write a full-length research paper that then gets submitted to like the Intel ISIF Science Fair, as well as the state and local science fairs, and the Virginia Junior Academy of Sciences. So I did an astronomy project, and I was one of the first people to come through that wanted to do an astronomy project, and we went through a very, very, very arduous process of trying to find an astronomer who was willing to work with a high school student. And so I actually worked with Jay Lockman, who's at the National Radio Astronomy Observatory, and we had a very challenging time interacting via email. This is still when email was sort of still getting big, you know. And so when I was approached as a graduate student to help with these high school projects, I thought of how important it was in my own career in terms of getting involved in research early and exploring a topic that you don't get to explore, as well as then going to college and knowing that's what I wanted to do and being able to talk with real astronomers, how important that experience was. So I said, yes, let's do it. And later we recruited Joanna, and she can tell you about herself. All right. On different types of bread, say. So it's something that is...
Done that.
Yes. So it's something that's relatively contained where you design the experiment and then you do it. So with astronomy research, however, because of the timescales involved with applying for and then obtaining data, which we all know can take a year or more before when you conceive of a project, apply for it, get the time, and then actually do the observations, and then actually process the data, are much longer timescales than a high school student can conceivably do. So we've actually been utilizing data that we have. So one of the projects came from a huge Spitzer Space Telescope survey in the outer disk, and these were the first images taken in that region, and we actually just had the students go through and find certain classes of objects in that region. So it's just like kind of like Galaxy Zoo type project to do. And so the way we've approached doing these high school projects is we take a data set and we figure out a subset of projects that could be done and that are scalable, and then we propose them to the students, so multiple different areas of astronomy, so data we have on hand, tools that we have available, and we let them pick what they gravitate to the most, but we sort of have them choose specific projects that we've worked out. Because one of the key things is that a lot of astronomy takes place in Linux and Unix, not in Windows or Mac. And so getting the students access to proprietary software, giving them appropriately sized hard drives to house data, things like that require some finagling. So we sort of designed the project a little bit ahead of time based on the resources that we can provide. And partnering with the school is really important. For all of our students, they give them loaner laptops that they actually take home. So we install all of the software we need to install or give them access.
Yeah, this year we actually installed Ubuntu on all of their computers so they can directly work with our Linux systems. So yay for...
Yeah.
I was really excited that they're working on Ubuntu already.
Yeah, and so...
And having exposure to Linux systems directly.
And so obviously what we've discussed is that some of the big barriers to research are learning a new computer system, a language that you're not used to. So we actually composed a set of tutorials that teach them how to do some very basic Linux.
Yeah, so I'm Joanna Corby. I am a graduate student as well. And I research chemistry in our galaxy primarily. So until about 1970, we didn't think that polyatomic chemistry could happen in space. Now we know there's more than 170 molecules, and we're finding new ones every year, and we don't know how most of them got there. And we know that they give us really important clues to the physics of the interstellar medium, the gas between stars. But we don't really know what those clues are yet because we need to figure out how they got there and what conditions they actually form in. So that's my research side. I did not do astronomy research as a high schooler, but I kind of actually was pushed into this project a little bit by my advisor, who had kind of volunteered and then said, "Ooh, you do it."
Donate.
Outreach was very important to me before starting my graduate work. I have always considered teaching as one of the two components of participating in academia, and I've been more interested in working with K through 12 programs than with college programs because I think that's where the real big problem in the U.S. education system is. One of the really big strengths of this program is that it gives students, I don't care if it's astronomy research experience, it gives them science research experience. And the way we handle science in the K through 12 level isn't really in touch with how science is done. And so I think it's really cool that they get exposure to how science is actually practiced and who scientists are. And something they should come away from the program with is that when they start school, like Rachel said, they should be able to talk to people who are graduate students, who are level, and understand that they are people with cool problems and cool questions.
Cool. So how do you go about picking a research project that's appropriate for a high school student, depending on whether or not they've had astronomy before or computer experience?
Yeah, so that's one of the big challenges. So the typical high school research project, to pick a really boring vanilla example, would be like growing mold.
Blah, 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 blah.
Blah, 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 blah.
That's my testing. All right, woohoo, everyone's back. Okay. Hi, everyone. Welcome to this week's Learning Space. I am Nicole Gugliucci, your CosmoQuest postdoc, and I'm joined by my co-host all the way this side. I never know.
I'm over here.
It's mirrored. I don't know what's happening. George is over there somewhere in the other hallway.
Yeah.
And so I'm with and I have with us a couple of my friends from University of Virginia, two graduate students. So weird, I can't think of you guys as students, because then, I don't know. You're my colleagues! I don't know. I'm like, that's weird, you guys aren't students, you're like real astronomers. This is Rachel Beaton and Joanna Corby, who are real astronomers.
That's a good thing.
I'm sorry, I'm tired. And we are going to be talking about their experiences working with high school students doing astronomy research, and how high school students can get involved in different types of astronomy research. There are a lot of different opportunities for that. So if you want to join in, you can ask questions on the YouTube page if you're watching on YouTube. If you're on the event page, I will try and watch that as well, or you can use the question and answer app here on Google Hangouts, so feel free to say hello, send a comment, ask a question, all that good stuff. So why don't we jump right into it? So, hello. Maybe you guys want to give just a brief overview of yourselves and the work you're doing at UVA.
You go first.
Sure.